Cosmology is now filled with speculative ideas: grand unification, inflation, quantum genesis. How testable are these ideas with terrestrial physics? If we ask the limit of lab physics, involving large accelerators, we can see that the Large Hadron Collider can instantaneously create temperatures of about 10 to the 16 or 10 to the 17 Kelvin. Phenomenal energies. Those are the temperatures that were present in the entire universe about a picosecond after the Big Bang. That, therefore, is the limit to which lab physics can ever verify or corroborate our theories of the universe. In the popular press, this has created some concern, because the Large Hadron Collider is not only able to simulate a very early phase of the universe, but also create instantaneous matter densities that are not that far from microscopic black holes. To understand the next phase of the universe, still the very early universe in a fraction of a second, but not the fantastically early era of inflation in the Planck epoch, we have to consider particles and radiation. Particles and antiparticles can readily be created from pure radiation. This happens in the lab and in physics experiments all the time. Those particles and antiparticles, when they meet, will annihilate to reproduce the same radiation that gave birth to them. In the early universe, we believe that particles and antiparticles, their mirror images in quantum properties, were present in essentially equal abundance. So the universe was a seething ocean of very high energy radiation and particles and antiparticles coming in and out of existence almost instantaneously. If the laws of physics were perfectly symmetric, there would have been exactly equal numbers of particles and antiparticles, because they're always created in pairs. This would have been electrons and anti-electrons, quarks and antiquarks, essentially all the fundamental subatomic particles and their antiparticle twins. In the theory of physics, if you have sufficient energy, then mass can be created by rearranging the equation E equals mc squared. So, hypothetically, about a microsecond after the Big Bang, the universe would have had a temperature of about 1 trillion degrees. That's the energy from which neutrons and protons can have their antiparticle pairs created spontaneously out of pure energy. Below that temperature, or after that time, such creation is not possible. The speculation is that there was a very slight imbalance in the amount of matter versus antimatter. This is hypothesized to have occurred in the grand unification era. Essentially, there's a slight asymmetry in the physics emerging out of unifying the forces. This imbalance was at the level of about 1 part in 10 to the 9. If you can imagine a bicycle wheel, a meter across, that's almost perfectly round, but skewed out of roundness by just 1 micron, that's how out of symmetry physics was in this early stage. Almost perfectly symmetric between matter and antimatter. But with this slight asymmetry, as the universe cooled, there would have been a very slight excess, by 1 part in 10 to the 9, of particles over antiparticles. When it cooled below the threshold temperature for producing quark and antiquark pairs, there would have been a very slight excess of quarks left over, as the billion quarks and antiquarks all annihilated. So you end up with a situation where there are 1 billion times more photons than particles, and that slight asymmetry represents the matter content of the universe. The same process would have occurred for electrons and anti-electrons a little while later. What the theory is seeking to explain is another profound and simple attribute of the universe: the fact that around us, and in the universe on large scales, we see matter and not antimatter. And we see about 1 billion photons for every particle in the universe. Those are the photons of the microwave background. Is there experimental verification of that statement? Yes, there is. Astronomical observations are quite sufficient to rule out antimatter on large scales. In the terrestrial environment, antimatter will annihilate with matter almost instantly, producing gamma rays that we would observe if it existed. But what about space, which is almost a pure vacuum? Almost, but not pure. Interstellar and even intergalactic space has small amounts of matter, particles. So if there were regions where there were anti-galaxies or anti-clusters on very large scales, the interfaces between those regions of antimatter and matter would produce enough gamma ray emission to be seen by orbiting satellites. These observations have been done actually a few decades ago, and so cosmologists have been confident for a couple of decades that there are no parts of the universe made of antimatter. Essentially everything we see is just one of the 2 flavors. Unification theories seek to explain that slight asymmetry and thereby account for why there are 1 billion photons for every particle and essentially no antiparticles. The next landmark in the history of the universe occurs in the first few minutes after the Big Bang. And this is very well understood physics, because these are temperatures and energies that can fairly easily be recreated in a lab, at least for short instants of time. In this era, protons and neutrons started fusing, but the fusion was counteracted by nuclei being ripped apart by the very high temperatures. Fusion, nucleosynthesis, the same process that occurs in the Sun, was therefore occurring in the entire universe. But the Sun and stars like it are stable. The universe, of course, was expanding continuously, so this fusion lasted barely 2 minutes. By the end of it, however, 1/4 of the mass of the universe had been transformed into helium, and a few other light elements like lithium and deuterium. It is a victory of the Big Bang model that it explains, with only one free parameter, the abundance of these light elements in the universe. The abundance of light elements is a profound test of the Big Bang model because deuterium, lithium, and helium are produced in quite different regimes in astrophysics. Stars both make and destroy lithium, while they only make hydrogen, and deuterium is not found in much abundance in stars but is found mostly in intergalactic space. Measurements in these quite different physical regimes all produce values that agree with a single parameter of the Big Bang model, which is the number of photons to particles. And this agrees with a matter abundance in the universe of about 4% of the critical density. This convergence of measurement and Big Bang theory was a great success of the model back in the 1970s and 1980s. From the time a few minutes after the Big Bang until just under 400,000 years after the Big Bang, the universe was simply an expanding and cooling plasma, cooling from a temperature of 10 million Kelvin down to about 3,000 Kelvin. When the universe reached this size, density, and temperature, it reached the point where electrons could combine with protons to form stable hydrogen and also helium atoms. This is called recombination. Recombination was connected to a second process called decoupling, whereby photons no longer interacted or scattered off the free electrons and were able to travel freely. 380,000 years after the Big Bang is therefore when the universe becomes transparent. From 380,000 years after the Big Bang to 100 million years or so after the Big Bang, the time is not clear yet, the universe was in a phase called the Dark Ages. It had cooled to below the temperature of the reddest red dwarf, so the radiation in the universe dimmed below the visible range to become invisible infrared wavelengths, essentially dark. Meanwhile, gravity had not had time to sculpt any objects. Mostly the gas was uniform. The variations that we see in the microwave background are tiny, 1 part in 100,000, and it took time for them to gradually grow into fluctuations that would collapse by gravity to form bound objects like stars and galaxies. Determining the exact time when the first objects formed in the universe, when the lights went on, and the end of the Dark Ages arrived, is the goal of the James Webb Space Telescope. The Hubble Space Telescope has reached the limit of its capabilities as it goes to about 100 million years after the Big Bang. Cosmologists are trying to push the Big Bang theory to the limit, and that means describing even earlier instants in the universe history. The absolute limit to our knowledge is the Planck era, 10 to the minus 43 seconds after the Big Bang. We have hints that inflation occurred 10 to the minus 35 seconds after the Big Bang. The next landmark is the era when particles and antiparticles almost perfectly annihilated to create a universe mostly filled with radiation with a very slight residue of matter. This happened after about a microsecond. The next landmark is the creation of helium, forming about 1/4 of the universe by mass, in the first few minutes after the Big Bang. Thereafter, the universe is a cooling plasma, and it goes into its dark ages. It takes perhaps 100 or 200 million years after the Big Bang for the first objects to switch on as light bulbs in the sky, stars and galaxies.